Well, in this video I'm going to look at the improved Euler method. Two steps of it applied to this simple little differential equation of y prime equals 2 cosine of x, y at 0 is 1, step size is pi divided by 4. And what I want to do is visually look at the improved Euler's method step by step, applying Euler's method to create this improved Euler method solution data points, just first couple, and then actually look visually at what's going on, and then a visual comparison between the results of 2 steps with the improved Euler's method compared to 2 steps of Euler's method. Hopefully give you a kind of a visual sense of how this is all working. So the graph of the differential equation that we're solving, the analytical solution, is on the screen as x goes from 0 to 2, but actually 0 to pi divided by 2, we're stopping at it up here. And first thing we're going to look at is applying Euler's method. Step 1, so you're going to apply Euler's method to right here, this, the initial condition when x is 0, y is 1 here. And you look at what Euler's method gives you. So there's one step of Euler's method. You can see the tangent line to the graph at the initial condition. Graph is concave down, so Euler's method, which is based on tangents to the graph, based on the differential equation, is going to be high over this little interval. And we can see it's off by a noticeable amount, but then pi divided by 4 is a pretty big step size. So that's what one step of Euler's method produces. Now what we want to look at next is step 2 of Euler's method, which would mean that you actually apply it here and would take you in this direction up to here. Since the y prime is a function only of x, the slope of that portion, that second step of Euler's method, is the actual slope of the tangent line to the graph of the analytical solution right here. It kind of looks like that. It's very simple because you got dy dx equals a function only of x and not of x and y to keep things simple here. You see the second step of Euler's method shoots you way up here. Analytical solution would have put you here, so it's off by quite a bit with step size this large, with this much downward curvature in the graph of the analytical solution. You have to have a much smaller step size for Euler's method to be even close to being accurate. So now we see step 2 of Euler's method cut in half. So you got the green line segment coming from step 2 of Euler's method has been cut in half. And we're going to use this down here to make an adjustment, we hope make a more accurate result. And we're going to literally attach this line segment with that going in that direction halfway up this first step of Euler's method. So we'll make an improvement down here. Let's watch us do that now. So that step, half of that Euler step up here, got redrawn down here. So the improved Euler's method correction, step 1, we had to go halfway up following Euler's method, and this improvement based on the direction that up here would have indicated. And the direction up here indicated said, well, things concave down, so maybe we take the direction we would have gone in up here and go back here and go in that direction, and halfway up, and maybe it'll be more accurate. Well, you can see that it is. It's off by less. It's low now, too. Even though the graph, the analytical solution, kind of gave down, this improved Euler's method is actually coming in a little low, and it's not off by as much as the Euler's method would have been. So a bit of an improvement there at that point. So we erase that, and then we went in here and applied Euler's method to this point right here, which does take you in the same direction as it would have up here, same x value. So there's Euler's method applied down here, the sort of Euler prediction for step 2 of the improved Euler's method. Now I take it from there way up to there, but takes you way off by almost as much as Euler's method did. But now we're going to use that result to make a correction. We're going to go up to the end here and see what Euler's method would have given us up here, and take that direction and apply it once again halfway down this red one-step Euler's method from here. Let me take a look at that. So there's the improved Euler correction. Now, what the correction is going to be is the up here going from, got the improved Euler's method going here, here to here, and then we applied Euler's method here, took us to there, looked at what direction Euler's method would have gone in from here. Well, down here the graph's actually leveling off. A relative max point we kept going there. So it's going to be a horizontal direction from there that Euler's method would have taken it. What we're going to do is take that direction, go halfway down in here someplace, and apply that length in that direction down here. Let's take a look at that. So that's what we did. So here's the improved Euler correction, step 2. That was to correct it by going from here, not way up there, but here over here. So from the end of the first improved Euler result, going up halfway, half of what the actual step size was, and then improved by going in this direction, which is the direction determined up here. So we'll erase that. So there you've got the improved Euler method, 2 steps. It comes in a little low, but not nearly as low as the Euler method was going to produce after 2 steps. In fact, we can draw that in there now. So here's Euler's method applied, right off here by quite a bit, not off by a whole lot, whereas the improved Euler's method came halfway up using Euler's method, made an adjustment, and from there halfway up using Euler's method, made an adjustment based on Euler's method, and gave us this result. So here we're actually not real accurate, but then that step size of pi divided by 4 is pretty large step size. If we used a much smaller step size, we would have done substantially better than what we did. So there's your comparison of the improved Euler and Euler 2-step, as I say, comparison.